Good day, students. Welcome to Mathgotserved.com. In this clip, we're going to be going over problems 1 to 5 of the Geometry Common Core Regents exam for August 2015. Don't forget that the transcripts to this video can be found on Mathgotserved.com under New York Regents. Alright, let's take a look at problem number 1. It reads, a parallelogram must be a rectangle when it's, and then we have a list of properties here. Diagonals are perpendicular, diagonals are congruent, opposite sides are parallel, and opposite sides are congruent. First thing you want to recall is that all rectangles are parallelograms. Okay, I'm going to write it in short here. All rectangles are parallelograms. Okay, but not all parallelograms are rectangles. Okay, so that's something you want to keep in mind. Now, that's what this question is asking here. It's asking for what condition is necessary for a parallelogram to be a rectangle also. All right, so what we're going to do here is we're going to take a look at two cases. We're going to draw a rectangle, which is also a parallelogram, and then we're going to take a look at and also sketch a parallelogram. The parallelogram we're sketching, we're going to make sure that it is not a rectangle. Okay, so how do we ensure that it's not a rectangle? Just ensuring that the angles are not 90 degrees, the angles of the parallelogram. Okay, so what we have here, we have a rectangle. This is a rectangle, but it's also a parallelogram, right? Because all rectangles are parallelograms. So rectangle and parallelogram. And this is a parallelogram and not a rectangle. Now, what condition is necessary for a parallelogram to be a rectangle? So what we're going to look for is properties that apply to just this special case of a parallelogram, namely a rectangle. Okay, if a property applies to both, that's not what we're looking for. We're looking for properties that apply to just rectangles, something that's unique, a unique property of a parallelogram that makes it a rectangle. Okay, all right, so let's exhaust the options here. Let's take a look at option number 1. Diagonals are perpendicular. So option 1, diagonals are perpendicular. Write that. Diagonals are perpendicular. Now let's take a look at this case, the case of the rectangle. Are the diagonals perpendicular for all rectangles? Let's take a look at this real quick. These are the diagonals right here. We can clearly see that the diagonals are not perpendicular. Okay, and if we take a look at the parallelogram over here, we'll see that the diagonals do not have to always be perpendicular. Okay, so the fact that the property does not even apply to rectangle, we don't even want to consider it, because we need the property that applies to rectangles and not all parallelograms. So diagonals perpendicular here, the answer is no. Okay, so let's even label our vertices A, B, C, D. A, B, and CD, A, B, and DC are not perpendicular. Okay, and in this parallelogram that is not a rectangle, the answer is no also. All right, now let's go ahead and take a look at the next property. Diagonals are congruent. Okay, so diagonals are congruent. Are these two diagonals congruent for a rectangle? The answer is yes. That's a property of rectangles. AB congruent to CD, the answer is yes. Is this the case? Okay, so all parallelograms which are rectangles must have congruent diagonals. All right, let's take a look at this case right here. Is AB and DC congruent? The answer is clearly no. AB is much longer than DC, even though this is a parallelogram. So is AB congruent to DC? The answer is no. So this is the condition that we're looking for. Our answer is option number 2 because diagonals of a parallelogram must be congruent in order for it to be a rectangle. Now let's just go over 3 and 4 just to make sure we understand what's going on here. For 3, it says opposite sides are what? Opposite sides are parallel. Does that apply to a rectangle? Absolutely. AC is parallel to DB and AD is parallel to CB. What is that special? Does it apply only to parallelograms that are rectangles? The answer is no. This is not a special property. Okay, it applies to what? It applies to all parallelograms. Check this out. This is parallel to that, and this is parallel to that. So if a parallelogram is a rectangle or not, that doesn't matter if you're looking at the parallelity of the opposite sides. So this is yes and yes. Remember, we're looking for the only properties that work for rectangles and not on some of the parallelograms that are not rectangles. Okay, let's take a look at option 4. Opposite sides are congruent. Opposite sides are congruent. Does this apply to some rectangles, namely some parallelograms, namely those that are rectangles, or does it apply to all parallelograms? Take a look at this situation right here. AC and DB are opposite and congruent. This side is congruent to that side. DA and BC are opposite and congruent also. So this side is congruent to that side. So the answer is yes here, but does this apply only to rectangles? The answer is no. Opposite sides being parallel, congruent, I meant to say, opposite sides being congruent applies to all parallelograms, regardless of if they are rectangles or not. Okay, so if you look here, DB is congruent to AC, and DA is congruent to BC. So yes, yes here. So we can clearly see that the unique property that separates the parallelograms that are rectangles from the parallelograms that are not rectangles, one of them is that the diagonals are congruent. And the other one, of course, is that all the angles are 90 degrees, which is applicable here, but is not applicable here. So the answer is option number 2. All right, let's take a look at problem number 2. It says if triangle A prime, B prime, C prime is the image of triangle ABC, under which transformation will the triangles not be congruent? So anytime you're thinking about congruency with transformation, the first word that should come to your mind is isometry. Okay? So the word isometry basically means iso means the same, metry means measurement. Okay? Isometry basically means that the lengths are preserved. The lengths do not change under the transformation. Okay? So basically what this question is asking here is which of these transformations is not an isometry? Which of these transformations changes the lengths or the size of the image? Okay, if that happens, then it's not an isometry, hence the transformation will not be congruent. Okay, so there's this really nice graphic on regentsprep.com that gives you a nice visual of the different transformations that there are and if they are isometries or not. What you want to remember is that dilation is not an isometry. This is not an isometry. Reflection, translation, and rotations are isometries. What does that mean? It means those transformations do not change the size of the object. Okay, it doesn't change the size of the object, but dilation does. Okay, so if you look at this grid that we have here, we can see that reflection is an isometry, These two reflections are isometry. Transformation is an isometry. Rotation is an isometry. But dilation is not an isometry. Okay? Hopefully that makes sense. If you think about dilation, what are you doing? You are stretching or shrinking the figure. Okay? All right, so if you go over this, can you see what the answer is? Reflection is an isometry, so will they be congruent? Yes. So this is not the answer. Remember, the problem is asking for which transformation is not congruent. In other words, is not an isometry. Okay? Translation is just a shift. It doesn't change the sign. Translation is an isometry, as you can see here. And we already did reflection. How about dilation? Dilate is to stretch. Think about the pupils of the eye. When they dilate, they get bigger, the size changes. Is this an isometry? No, it is not congruent. The image is not congruent to the original. So this is the answer that we're looking for. How about rotation? Is rotation an isometry? It certainly is. You're just spinning the object. You're not changing the size, okay? So this is not an answer I'm looking for. The answer is number 3. The transformation that the image is a different size or is not congruent to the original object. Okay, let's take a look at number 3. It says if the rectangle below is continuously rotated about side W, which solid figure is formed? Okay, so before we answer this question, let's do a real quick review of our different 3D shapes in geometry. We have a pyramid. It could be a square pyramid or something else. So let's just sketch our pyramid. Think about the nice little structures you see in Egypt. That's a pyramid right here. A rectangular prism. It's something like this. There's a prism where the bases, identical bases are rectangles. It goes a rectangular prism. A cone. Think about an ice cream cone, circular base. And then a cylinder is a prism where the bases are circles, right? So which of these will be result when you rotate this figure about the side W? Okay, so let me sketch the rectangle on the side here. Now, since we're rotating this rectangle about side W, this is an axis of rotation. All right, so what does that tell you that the base is going to be? If you're rotating this rectangle about this line, side W, you're rotating it like this, the base is going to be circular. Okay, so we can eliminate 1 and 2 because these are rectangular or they have quadrilateral or polygonal bases. So it's either option 3 or option 4. Now let's go ahead and carry out the animation. You have to visualize this. This point, what's going to happen with this point? This point is going to be equidistant from this line as it rotates around that axis. Part of my sketch right here. And then how about this vertex right here? What's going to happen is going to maintain this distance as it itself rotates around this line. Okay, rotates around this line. Now, what kind of 3D object are we creating here? This is clearly a cylinder. Okay, so we can see that the answer is option number 4. Now, how do you create a cone? The problem doesn't ask for it, but let's just go over that because this is really cool. If you have a right triangle and you rotate a right triangle around this altitude right here, what you get is a cone. All right, so if you rotate this like this around this side, let's call it X. If you rotate it around this side, what do you get? You get a nice little cone. All right, so that's how you create cones by rotation, just by rotating right triangles. All right, and you create a cylinder by rotating a rectangle about its side. All right, so the answer is option number 4. Okay, let's take a look at number 4. It says, which expression is always equivalent to sine x when when x is between 0 and 90 degrees? So to help us answer this question, let's go ahead and draw a right triangle. What do we know about right triangles? We know that other than the 90-degree angle, the other two angles are less than 90 degrees and greater than 0. Okay, so let's call this angle. Let's do this in blue. So this is angle x. Okay, so this is angle x, and this is 90 degrees. What is the measure of this angle? This angle is known as the complement of this angle right here, because when you add these two angles together, you get what? You get 90 degrees. Added to this 90, you get 180 degrees. The sum of angles in a rectangle. So this is x and this is 90. This is automatically the complement of this, which is 90 minus x. Okay? So if you add all these together, you should end up with 180 degrees. So now that we have the setup, let's go ahead and inspect this trig function we have here. So we are told that sine x is equal to one of these. 1, 2, 3, or 4. Which of them is sine x equal to? Now, if we're using x as our reference angle, let's call this side right here A. Let's call this leg B, and call this C. If we're using this as our reference angle, this side becomes the opposite. And this side right here is the hypotenuse. And this is the adjacent. Okay? So for sine, what is the ratio that relates sine of this angle to two sides of this triangle? We're going to have to use SOHCAHTOA, right? SOHCAHTOA. Now, S is for sine, so what does SOHCAHTOA tell us? It tells us that sine theta is equal to the opposite divided by what? The hypotenuse. So in this case, what is sine x? Sine x is the opposite A over hypotenuse, which is C. All right? Now, let's take a look at cosine. What is cosine theta from Ka? Cosine theta is adjacent over hypotenuse. So what is cosine x? Cosine x is the adjacent, which is B, divided by the hypotenuse, which is C. Are these two the same? The answer is no. So we can eliminate option 4 because cosine x and sine x are not equivalent. They are not the same. We're looking for something that's equivalent to sine x. Now, how about we switch to this angle right here, 90 minus x. If this is our reference angle, guess what? Our hypotenuse stays the same, but our adjacent becomes the opposite because this is the side that's opposite this complement of x, and this is the adjacent to that angle. So it's going to change our ratios. Now, what is sine of 90 minus x? 90 minus x, the complement of x. The sine of x using opposite of a hypotenuse, is going to be b, the opposite of this angle, divided by the hypotenuse c, which does not change. Now, what is cosine of 90 minus x? Cosine of 90 minus x using Ka is the adjacent, which is a, divided by hypotenuse, which is c. Now, take a close look at these ratios that we have right here. Do you see a pattern? Well, what you notice is that sine of x is the same as cosine of 90 minus x. These two are the same. And then, if you look further, you will notice that cosine of x is equal to sine of 90 minus x. They are both b over c's. These two are the same. So what's the conclusion here? if you have a right triangle, sine of an angle theta is equal to the cosine of the complement of theta. Okay, what is the complement of theta? It is 90 minus theta. Remember, complementary angles are angles that add up to 90 degrees. So what is the answer here? We are asked for what is equivalent to sine x. Sine x, which is A over c, is equivalent to cosine 90 minus x, which is A over c also. All right, so our answer is option number 1. All right, let's take a look at problem number 5. It says in the diagram below, a square is graphed in the coordinate plane. So we have the square right here on the coordinate plane. The question is, a reflection over which line does not, remember not, carry the square onto itself? So just a real quick tip when you're dealing with reflections along lines and carrying an object to itself. So quick tip is reflection along the line of symmetry, of an object. Guess what it does? It carries the object to itself. Okay, carries the object to itself. What does it mean to carry an object to itself? It basically means that you end up with exactly what you started with. Okay, so if an object has line or lines of symmetry, if you reflect that object about that line of symmetry, you end up with exactly what you started with. Okay, so what I'm going to do here is I'm going to draw the lines of symmetry of our nice little rectangle here. We have 5 lines of symmetry for this rectangle right here. Basically, a line of symmetry is a line that divides a figure into 2 identical parts. Okay, so let's go ahead and draw lines of symmetry here. All right, so the first line of symmetry, let's draw the diagonals. Okay, so we have the diagonal here, that's 1. That's a line of symmetry. This is the other diagonal right here. That's another line of symmetry. And then we have the medians. Mid-segment, sorry, I meant to say the mid-segment. Medians are for triangles. So the other 2 lines of symmetry are the mid-segments of the square. Basically, the lines that bisect the square vertically and horizontally. Those are the mid-segments, and they are also lines of symmetry for the square. Okay, so what I'm going to do, I'm going to go ahead and color code this so we can find the individual equations of these lines of symmetry, because these are the lines that upon reflection the square is carried onto itself. Okay. Okay, so I've color-coded my lines of symmetry, the lines that upon reflection the square is carried onto itself. Now, which of these options does not match any of these? Any of these equations that do not match the equations of these lines I've drawn here are going to be result in reflections where the square does not end up upon itself. Okay, so let's take a look at the first option, the line x equals 5. Now, what does that line look like? Remember that your x lines are vertical, okay? They're vertical. Let me write that again. They have undefined slopes, so remember your x lines have extreme slope, they go down. And your y lines have, if you have y equals to a number, they're horizontal, okay? So 1 and 2, you have x equals to a constant and y equals to a constant. Anytime you have equations like this, you have horizontal or vertical lines. The x are vertical, they have extreme or undefined slope, and the y's are horizontal, they have zero slope. All right, so the line x equals 5 is a vertical line that goes through x equals 5. Okay, so let's look at our coordinate system here. This is 0, 1, 2, 3, 4, 5. So the line we were talking about basically intersects, it overlaps this side right here. Okay, all right, so if you take a look at that line, is it a line of symmetry of the square? The answer is absolutely not. So what happens when we reflect this square about this line? Does it carry the square onto itself? The answer is no. If I reflect this square about this line, all these points here go to the right, and then we have a situation like this. A little bit bigger, down. All right, so is that square overlapping the other square perfectly? Let's make it red. The answer is no. So we can clearly see that our answer is option number 1. Okay? Now, I just want to go over these other options here just to make sure you really understand what's going on here. The line y equals 2 is a horizontal line that intersects the y-axis at 2. Okay? So look at this right here. That's 2 right there. What is the equation of this horizontal line? The equation of this horizontal line is y equals 2. It is a line of symmetry. So what does that mean? It means that if you reflect along this line, this square will be carried up onto itself. Okay? So because it's a line of symmetry. Now how about the line y equals x? The line y equals x is a line with a slope of 1 and a y-intercept of 0. Okay, so if you start from the origin, which has a y-intercept of 0, and you rise 1 and run 1, guess what? You end up with this diagonal right here. This diagonal is a line of symmetry of the square. Y equals x. What does that mean? If you reflect the square along this line, it carries the square onto itself. Nothing is changed. Okay, so this is a line of symmetry, so it's good. Now how about x plus y equals 4? Let's take a look at that. X plus y equals 4 is, in order to make this easy to graph, I will get y by itself. Okay, so we subtract x from both sides, and we have y equals negative x plus 4. Now, if I want to graph this line, I just need the slope, which is m, the coefficient of the x-axis, negative 1 over 1, and b, the y-intercept, which is 4. Let's go ahead and graph this line. This is your x-axis. You start from 1, 2, 3, 4. That's your b, 4. You rise negative 1, which means you fall 1, and you run 1. Okay? That takes you to this point. Wow, look at this. This is the second diagonal of the square. Okay? So the equation of this line is x plus y equals 4, or in slope-intercept form, y equals negative x plus 4. If you reflect this square along this diagonal, is it going to carry up onto itself? The answer is yes, absolutely, because it is a line of symmetry. Okay, so this one works perfectly. So the only line that does not carry this square onto itself upon reflection is the line x equals 5. Now, had it been that line where x equals 2, guess what? It will be perfect because it's one of the mid-segments of our square. Okay? So bottom line, remember that reflection along lines of symmetry of an object carries the object onto itself. You end up with exactly what you started with. Thanks so much for taking the time to watch this presentation. We really appreciate it. If you found the contents of this review beneficial to you, please give us a thumbs up. We'll appreciate your positive feedback. Do not forget to subscribe to our channel for updates to the remainder of this review series. If you have any questions about the Geometry Regents exam, just include it in the comment section below, and we'll be glad to help you out as soon as possible. More clips can be found on mathgotserved.com. Thanks again for watching, and have a wonderful day.